This lesson will explore how to use finite differences in order to identify both the leading coefficient and the degree of any polynomial that's given to you in a table format. So I'm going to start with this question here that I think is probably about as hard as these are likely to get, and we'll look at using a spreadsheet to use the finite differences method that we already explored. So again, over here, I'm just going to put in the x values. Didn't really even need the x values, honestly, but we're going to need them for something we're going to do a little later, so that's fine. And then the y values here, okay, right? So 953, 329, 79, 11, 5, 13, 59, 239, and 721. Now, finite differences, what do they tell you to do? They tell you to go to the next column, right? And starting at the bottom, take the bottom number, subtract the one above it. Okay, so for example, in this box, I'm going to write 721 take away 239. Now, because I'm using a spreadsheet, and this is the way I suggest you do these questions as well, we don't actually have to type in the numbers, right? What we could do instead is type in the cell addresses. So watch as I do this instead. Equals B9. Okay, B9 is this box where the 721 is, and then I'm going to subtract B8, right, which is the one right above it. Now, the reason you'd want to do it this way is because once you have it as this, you can just copy this and paste it into all the layers above. And you look at the formulas, right? This one's B9 take away B8. This one's B8 take away B7. B7 take away B6, and so on and so on and so on, right? And you can see that my first differences category or column is right here. Clearly, these first differences are not constant, which would reflect the idea that this is not a linear function. So we could do it again. Now, actually, in Google Sheets at least, when you paste this formula over here, it automatically brings the right cells with you. Right? Because relative to the two primaries, this is still in the same place. It's one left and one down, right? So over here, I'm going to go C8, take away C7. I'm going to do this above it, and above it, and above it, and so on. And you can see that once again, the third column is not constant, so we don't have a quadratic. In the third column, so again, we'll copy our formula, paste it again. Still not constant, and in our fourth column, we notice that they are all constant. Now, this is definitely proof, so remember, this is first difference, this is second, third, and this is fourth. Because the fourth differences are constant, therefore the function is quartic, which is to say degree 4. Now, I know the lesson sort of stopped there, but I wanted to add that once you get the which column is constant, you can actually also figure out the leading coefficient. And I'll just show you quickly how to do that. If it's the first difference that's constant, the difference equals the a value. Okay, so you're not going to get one of these questions anyway, so it doesn't really matter. In the second difference, the difference divided by 2 equals the a value. Okay, so the leading, let's not say a value, let's say leading coefficient. Okay, so suppose I found out that everything in the second column was an 8. That would mean that the function that had created that table must have started with a 4x squared, right? Because you take the constant differences of 8, you divide them by 2, and that gives you your leading coefficient of 4. Now, in your third column, you do the difference divided by 6, and in your fourth column, you do the difference divided by 24. So in our example, we're going to take this 72, divide it by 24, we find that it is 3, which means the leading coefficient of my polynomial is a 3. Okay? So what I know about this quadratic is it has to start with, not quadratic, quartic. This quartic must start with 3x to the power of 4. Okay? So not only do I know it's fourth degree, I know that the leading number is a 3. And once again, just to summarize, if your first differences are constant, that is, whatever that constant is your leading coefficient. So if this column were all 7s, then my function is 7x. This column, in the second column, if they're all constant, you can divide the number by 2, and that will tell you what the leading coefficient is. In the third column, you divide by 6. In the fourth column, you divide by 24. Now, we're not going to go beyond the fourth for our course, but I mean, if you did need to go beyond the fourth, there is a pattern here, right? 1, 2, 6, 24. The next one would be 120. And maybe if you've taken data management, you might recognize what this pattern is. But for now, no need to worry about it. We just think about, just remember, just take this down as a note somewhere. Divide your fourth difference by 24, third difference by 6, second difference by 2, first difference by 1. Okay? And that will work for finding the leading coefficient. Now, there is a second method that I want to show you for how to do this, which I think is even better. Okay? And this comes back from GeoGebra. So once again, GeoGebra Classic 5, I strongly recommend you download this program and use it. It's extremely useful for what we're doing. Very, very helpful for just about anything related to advanced functions. One of the things it has in it is a spreadsheet. So if you look under View here, and then under View, you hit Spreadsheet, and then once again, we can type in the values from our function, right? So I'm going to take these values, and I'm going to paste them over here. So look, you see -4 and 953, -3 and 329, etc., etc., right? All our values are in the GeoGebra spreadsheet. Now, when you are looking at the spreadsheet in GeoGebra, so look here, right? I just clicked the graphics area, and you can see I have a bunch of tools related to graphics. When I click the spreadsheet area, I get different tools, okay? And this is what I need to use. So I'm going to highlight the section of data that I'm interested in, and I'm going to do what's called a two-variable regression analysis. Now, what does this mean? It means it's going to plot a bunch of dots on the screen, and then it's going to try to figure out what function goes through all the dots, right? So two-variable, okay, so I'm going to hit Analyze. Now, just to make sure we can see it, I'm going to make this graphics view a little smaller. And this is what we're looking at, right? Sequence of dots. Now, of course, the regression model to choose will depend on what you think the shape looks like. So if I choose a linear model, you can see the linear model is basically junk, right? I mean, it goes through 2 points. It's a very, very poor model of what these dots are. A sinusoidal model, right, like a trig model, it can't even do, right? I mean, it just says, like, I mean, I give up. I don't know how to do that. An exponential model, you can see, is also junk. But a polynomial model, right, is not bad. Now, we know that this function, because we just did the work, is not degree 2, right? And you can see that the best model that it can make that's degree 2 isn't good enough, right? And a degree 3 model is kind of like even worse, right? It doesn't do a very good job. But a degree 4 model is actually quite perfect, right? You see a degree 4 model fits it exactly. And the reason why I think this is quite good, right, is because I'm going to right click here and go copy to graphics view, okay? Now I can shut down the data analysis, I can shut down the spreadsheet, and I can actually look at this function from the perspective of like a regular graph. And you can see that it goes through every single one of these points perfectly. And not only that, it gives me the power, which is a 4. It gives me the leading coefficient, which is a 3. You can see that the 3 that we thought from earlier is confirmed. But GeoGebra goes a step further. It also finds the entire function. Now, in our course, I'm not going to ask you to find the entire function, but it's powerful to be able to do that, right? If you have a bunch of dots, GeoGebra can generate a function that goes through those dots, okay? So in summary today, when you are using a table of values to find the degree of a polynomial, you do the first differences over and over until you cannot go any further, until you get them to be all the same. And the column in which you get them all the same tells you the degree of the function. Once you have that, you can divide the first difference by a certain number, again, a 1, a 2, a 6, or a 24, in order to arrive at the leading coefficient. Alternatively, you can use GeoGebra's spreadsheet view, right, to do a two-variable regression analysis of the data, and then you can use that in order to generate a polynomial model, and you can basically cycle through. Is my polynomial degree 2? Well, that's not a very good fit. Degree 3, that's a better fit. Degree 4, that's a perfect fit. It's definitely degree 4, right? And you can see that's GeoGebra manages to do that. The advantage of using GeoGebra is not only does it tell you the degree and the coefficient, it also tells you the actual entire function, which you can imagine may be useful, for other things later on in the course. So when you go and open the assignment and the question says, what is the value of the leading coefficient? Now you should know how to do that. Please remember, any questions, of course, post to the forum, and I'll get back to you always within the next school day.